Section 4.3, what derivatives tell us. Let's begin with this first definition of increasing and decreasing functions. Suppose a function is defined on an interval I. We say f is increasing on I if f of x2 is bigger than f of x1, meaning y2 is bigger than y1. Whenever x1 and x2 are in I and x2 is bigger than x1. We say f is decreasing if f of x2 is smaller than f of x1 whenever x1 and x2 are in the interval I and x2 is greater than x1. So when something is increasing to decreasing, I always think of it as you read math, as you read English, read from left to right. So we see that we're going up when something is considered to be increasing, and we're going kind of down the stairs when something is decreasing. Theorem 4.7. Test for intervals of increase and decrease. Suppose f is continuous on an interval I and differentiable at all points of I. If f prime of x is greater than 0 at all interior points of I, then f is increasing on I. If the derivative f prime of x is less than 0 at all interior points, then it's decreasing. So increasing, we go up from left to right, and decreasing, we go down from left to right. Now, if the derivative is greater than 0, meaning if we have a positive derivative, then it's considered to be an increasing part of our graph, our function. If it's a negative answer, then we say it's decreasing. And when I say negative, it's when you test some point within the derivative, because that's what our definition says. Now let's take a look at an example. We're not going to do all the examples in this section just because it would be such a long lecture, but you can always find all these questions on your textbook. So let's take a look at this example 1. Sketch a graph of a function f that is continuous on -infinity to infinity and satisfies the following conditions. 1. F prime, our derivative, is greater than 0 from -infinity to 0, from 4 to 6, and from 6 to infinity. 2. The derivative is less than 0 from 0 to 4. At f of 0, it's undefined, and f prime of 4 equals f prime of 6 equals 0. Okay, so here's a little hint. A graph will change direction when the first derivative equals 0. Also, the graph is decreasing when its derivative graph is negative. Also, a graph is increasing when its derivative graph is increasing. All right, so let's take a look at our graph. Let's draw a really rough sketch. And let's label some points. So we have from -8 to 0, 4 to 6, and 6 to 0, and also 0 to 4. So we have infinity, -infinity, to 0. Then we have from 4 to 6, 4 to 6, and then infinity. So 4, 6. Now we said that, let's highlight some values, that our function is increasing from 0 to infinity, from 4 to 6, and from 6 to infinity. And our function is decreasing from 0 to 4. All right, so we don't know much what's going on, but we know what's happening based on our derivative. And we know that our graph is increasing, so going up on those values where I have those blue or those labelings. So something is happening to where it's going up and up. Now, based on the second piece of information, we're told that it's decreasing from 0 to 4. At f prime of 0 is undefined. So this would make this a critical point where it's neither a max or a min. It's kind of maybe a peak. And we're told that f prime of 4 and f prime of 6 are both equal to 0. So that means that our slope is 0. So for this one, it could mean that there is some type of minimum. For this one, it's going up and down. Maybe it's some sort of little curve here. Because based on this information here, all we know is that I have a horizontal line. Because the derivative is equal to 0. Now, this is a very rough sketch of the information given, and you can take the liberty to move this up or down however you wish. But based on what we have, all we know is when the graph is going up and down and where we have some peaks. I'm going to go ahead and skip example 2. Theorem 4.8, the first derivative test. Assume f is continuous on an interval that contains a critical point c, and assume f is differentiable on the interval containing c except perhaps c itself. If f prime changes sign from positive to negative as x increases through c, then f has a local maximum. If the derivative changes from negative to positive, then it has local minimum. If f prime is both positive on both sides near C or negative on both sides near C, then it has no local extreme value at C. Let's do this example. Using the first derivative test, consider the function f of x equals 3x to the fourth minus 4x cubed minus 6x squared plus 12x plus 1. A. Find the intervals for which f is increasing and those on which it is decreasing. Okay, so to answer this question, what we have to do is find the derivative, set it equal to 0, and find those values for which it equals 0, and then plug in some values in between to see if it's increasing or decreasing. All right, so let's start with the derivative. Our derivative using power rule would be 12x cubed minus 12x squared minus 12x plus 12. All right, we can factor out a 12, and we're left with x cubed minus x squared minus 12x plus 1. And then we can continue to factor by grouping. So let's factor by grouping. You get 12, and we're left with x squared minus 1, x minus 1. That factors to be x plus 1, x minus 1. So we can write our derivative to be f prime of x is 12. X minus 1, we have 2 of them, so squared, and x plus 1. Okay, we found our derivative. Let's set our derivative equal to 0. So that we have 12 times x plus 1 times x minus 1 squared. We set that equal to 0. We're left with x is equal to negative 1 and x is equal to 1. All right, so let's go ahead and make a chart as to where we can test our critical points. So these are our critical points. And we're going to test numbers in between. So I have negative 1 and 1. I want to test numbers in between to see if they're range is positive or negative to see if it is an increasing or decreasing part of our function. So remember our formula, if our derivative is greater than 0, which means positive, then we have an increasing part of our function. And if our derivative is negative, less than 0, then we know our function is decreasing. That's based on our theorem. So let's test some points. Let's test, for example, x equals 0, x equals 2, maybe x equals -2 to test. And pick points that would be easier to work with. So 0 is a good one to work with if it's possible. So let's plug in 0 into our derivative so that we have 12 times 0 plus 1, 0 plus 1 squared. We're left with 12 times 1 times 1 squared is 1. So all we care about at that is positive. So at 0, we got that it's positive. Let's go ahead and continue with -2. So 12 times -2 plus 1 times -2 plus 1 squared. You get 12 times -1 times -1 squared, which is just 1. So we're left with -12, which is negative. So at -2, we tested and it's negative. And at +2, we're plugging this into our derivative, f prime of -2. Our answer, well, let's figure this out. 12 times -2 plus 1, -2 minus 1 squared. We get 12 times -1. We get -3 squared, which is 9. Did I make a mistake? When I did it on my notes, I have something else. Let me try again. Oh, we already did -2. We're testing now +2. That's what I did. All right, +2. We get 12 times 2 plus 1 times 2 minus 1 squared. We get 12 times 3 times 1. We get a positive number. That's all we care about. So, based on our theorem, we said that on our first derivative test, if we change sign from positive to negative or change signs from negative to positive, we have a local extrema. Particularly if it changes from positive to negative, we have a maximum, and if it changes from negative to positive, we have a minimum. So here we see that we're changing from negative to positive, just in that range, only from that part. So we can say that there we will have a local minimum. So we have a local minimum at x is equal to -1. Why is that again? It's because we went from a negative to a positive within those boundaries in -1. Now, if we look forward from 1, on the left it has positive, on the right it has positive. So we would assume that there is no extreme value at that critical point of 1. So there's no extreme value at x equals +1. All right. There's another example for you to look at. Theorem 4.9. Local extremum implies absolute extremum. If f is continuous on all interval I that contains exactly one extremum c, f is a local maximum at C, then FC is an absolute maximum of F on I. If a local minimum occurs, then F of C is an absolute minimum on F of I. So it would make sense that if there's only one extremum, exactly one, if there's only one, then it's an absolute type of minimum or maximum. I'll let you try example 5. Next definition, concavity and inflection point. Let F be differentiable on open interval I. If F prime is increasing on I, then F is concave up on I. If F prime is decreasing on I, then it's concave down. If F is continuous on C and F changes concavity at C from up to down or vice versa, then it has an inflection point at C. All right, so let's talk a bit more about concavity. Concavity is different from increasing to decreasing. So increasing is when we go from left to right up. Decreasing is we go left to right down. Now let's talk about concavity. So I can have, let's talk about concave up. I could have a situation where it's increasing and decreasing and they're both concave up. So increasing means it goes from left to right up. Decreasing means it goes from left to right down. Concave up, I would think of this as it can hold water. Though this is something to do with the meaning, I always think of it like a spoon. It can hold up water. So concave up, when it's increasing, would look like this. Concave up, when it's decreasing, would look like this. Meaning if you were to imagine liquid, it can be held by that concavity up. Concave down would be if I'm decreasing or if I'm increasing would mean it can't hold up water. So it would go like this and like that. That is concave up. If you think about it, it would be like holding a spoon upside down. And if you try to eat cereal or your soup or sip on your hot tea with your spoon upside down, you can't hold water. So that is how I think about concavity. Now, I remember I would always switch up increasing and decreasing with concavity. They're very different, but they're still parts of our functions. So be careful if you catch yourself confused, think of a spoon for concavity. Theorem 4.10. Suppose f double prime, so the second derivative, exists on an open interval I. If your second derivative is greater than 0, meaning positive, then it's concave up. If your second derivative is negative, less than 0, then it's concave down. So again, concave up, if we draw a little picture, would be like this or like this. It can hold a spoon. Hold liquid. Concave down would be like this or like that. Example 6. Sketch a function satisfying each of the set conditions on some interval. So first we have the first derivative is greater than 0 and the second derivative is greater than 0, meaning positive. So for A, that first derivative being greater than 0 means it's increasing. So all this says is my points start down and go up, right? Now my second derivative is also positive, means it's concave up, which means it can hold liquid. It's like a spoon, right? try it better. There we go. You would be able to scoop up some liquid. Now for b, we have our function is decreasing. For our derivative is greater than 0, so it's increasing. So it goes from a lower point to a higher point. But our derivative, our double derivative, second derivative, is less than 0. So it means it's concave down. So it would be like an upside down spoon. So that is our A and our B. Now C, which function f or g could describe a population that increases and approaches a steady state of t equals infinity? All right, so for t equal infinity, if you recall chapter 2, way back when, it would be when we're approaching some type of horizontal asymptote. So if we take a look at these two graphs, the first one, we see it's going to keep going up, 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 up forever. If it's positive with concave up, it's going to go up forever. Now, if it's positive, increasing concave down, it's going to slowly reach a limit. So for C, our answer for that would be B would reach some type of horizontal asymptote. So that can be an example of a population that approaches a steady state. Example 7. Detecting concavity. Identify the intervals on which the function f of x equals 3x to the fourth power minus 4x cubed minus 6x squared plus 12x plus 1 is concave up or down. Then locate the inflection points. All right, well, if I look at this problem, it's the same one we did in example 3. So for that one, we already found our first derivative. Now, because it's asking for concavity, this tells me we have to find the second derivative. All right, so let's find the first derivative and the second derivative. We know the first derivative, but I want to avoid using product rule, so let's recall our first derivative. So I have f prime of x is equal to, let's use power rule one more time. We get 12x cubed minus 12x squared minus 12x plus 12. We can factor out a 12, and we're left with x cubed minus x squared minus x plus 1. Let's take our derivative. So that we have 3x squared minus 2x minus 1. And we can factor that trinomial so that we can have 12 times x plus 1, 3x plus 1, and x minus 1. So that's our second derivative. So let's write those down. Our first derivative from example 3, we said was 12x plus 1 times x minus 1 squared. And our second derivative, which we could have gone from the first derivative, but since we factored it, I didn't want to use product rule, so I took the derivative again and just followed using power rule. Our second derivative is 12 times 3x plus 1 times x minus 1. Now our question is, find the intervals for which the function is concave up or down, then locate the inflection points. Okay, to do so, I have to do the same process we did for our increasing and decreasing function, but for our second derivative. So I want to set our second derivative equal to 0. And solve. So we have 12 times 3x plus 1 times x minus 1 equal to 0. We're left with x equals negative 1/3. and x equals 1. So I have negative 1/3 and 1. Now I want to test points in between. Maybe a point like 0, 2, and negative 1, for example. Once you test some points, you'll see that when you plug in something like negative 1, well, let's go ahead and do that. So I have 12 times 3 plus 1 is 4, negative 1 minus 1 is negative 2, it's negative 2, so I have 12. Let me try again. So I have 12, negative 3, that was a mistake, negative 3 plus 1, and then negative 2. We're left with negative 2 times negative 2, it's positive 4, times 12, we get 48. So it's positive. When we test 0 into our second derivative, we get 12 times 1 times negative 1, we get a negative. And when I test 2 into our second derivative, we get 12 times a positive times a positive, we get a positive. All right, so we see that our inflection points are at negative 1/3 and 1. Now we see that it's concave up on those intervals, and on that middle interval, it's concave down. So to answer our question, identify the intervals for which the function is concave up or down. You can say our function is concave up on the intervals of negative infinity to negative 1/3, and concave up also from 1 to infinity. It's concave down from negative 1/3 to 1. Theorem 4.11, second derivative test for local extrema. Suppose f double prime, so second derivative is continuous on an open interval containing c with f prime of c equals 0. Now what we're saying here is if the second derivative is positive, then it has a local minimum. If our second derivative is negative, then it has a local maximum. If our second derivative is 0, then the test is inconclusive. It may have a local maximum or a local minimum, or neither. It can be just like an just like a weird change of direction, but not necessarily a maximum nor a minimum. All right, so let's go ahead and do example 8, and part A is that same example we've been doing. So use a second derivative test to locate the local extrema of the following functions. All right, so to help us get started, we have first derivatives and second derivatives already accounted for. So this first one, f of x equals 3x to the fourth minus 4x cubed minus 6x squared plus 12x plus 1 on the interval from negative 2 to 2 is the same example from part 3, or example 3. Okay, so our first derivative was 12 times x plus 1 times x minus 1 squared. And with that, we got some critical points. by setting our derivative equal to 0, and our critical points were positive 1 and 1. And then we found the second derivative, which was 12 times 3x plus 1 times x minus 1. And from there, we found some points of inflection, which is where we change concavity when we set our second derivative equal to 0. So we got x is negative 1/3 and 1. All right, now let's put this all together to locate an extrema. Now, based on what we have on our theorem, if our second derivative is positive, then it's a minimum. If our second derivative is negative, then it's a maximum. So let's go ahead and test these critical points, because these numbers come from when we set our derivative equals 0, thus our critical points. And I'm moving very slowly because it's kind of a lot to take in, and they kind of all just depend on one another. So we're going to test the critical points, which is when our derivative is equal to 0, into our second derivative. Now, why do we do all of this? We do all of this because we're trying to find minimums and maximums without having to go through the trouble of graphing. So it's an alternative, and not necessarily to just avoid the trouble, but it's another way that we can reinforce our understanding into the second derivative. All right, so f double prime of, we're testing these points, of 1 is, so we plug in 1 into our first derivative, into our second derivative, we have 12 times 3x plus 1 times x minus 1. We have 12 times 3 times 1 plus 1 and 1 minus 1. And that gives us 0. So we're left with 0. We plug in negative 1 to our second derivative. We have 12 times 3 times 1 plus 1 and negative 1 minus 1. We're left with 12 times 4 times negative 2. That's a negative. Same mistake I made before. We get negative, positive 48. So it's positive. So what do we get from this? This one is inconclusive. And this one, because it's positive, what does it say? If it's positive, then we have a minimum. So we can say from our function that we have a minimum at x equals negative 1. That's so cool, right? I think it's exciting to see how one thing kind of relies on the other to get to a conclusion. So let's quickly run over it again. We can see when a function is increasing or decreasing, so going up or down from left to right, based on our first derivative. Our first derivative tells us when our graph is going up or down at certain points. Now, these cutoff points are found when our derivative is equal to 0. Those are called critical points. Now, in addition to all that, we also learned about I want to get to concavity. about concavity, which is just the way our graph looks. Now, concavity and increasing and decreasing are different. Remember, think of it as a spoon, whether it can hold your soup or your cereal or not, whether it's facing up or facing upside down. If our second derivative is positive, then it's concave up. If our second derivative is negative, then it's concave down. And we can put this all together to find minimums and maximums, because remember that first derivative does help you find a local maximum or minimum, but it can be misleading because there can be values that are not necessarily minimums and maximums, but may algebraically seem to be. So if your second derivative is greater than 0, it's a minimum. If your second derivative is less than 0, meaning negative, it's a maximum. And if it's equal to 0, it's inconclusive. So here we have our function. Now, let me draw this function we've been working with this whole time. We do a really quick sketch. So we have these critical values at -1 and 1. Our graph actually looks something like this. So we would see that, yeah, you're right, we only have one minimum at x equals -1. This right here, it just kind of changes concavity, not necessarily a maximum or a minimum. It's not a local extreme value. So cool. All right, that was 4.3. Thank you.